Next up, we have Dr. Michael Barros from the School of Science and Computing, and Michael is going to talk to us about a theoretical new treatment of Alzheimer's using wireless optogenetics nanonetworks. Thank you, Michael.
Thank you, Ashley. So we have the TSSG Brain Initiative. We're trying to understand the brain, propose new methodologies how to treat new disease and do some EI as well. And here, when I say theoretical new treatments, don't take it too ready. It's far away from ready. Actually, even theory is not ready. But I would like to share with you what's going on in my research. So basically, Alzheimer's actually, it breaks, right? Everybody here, when you see some person with Alzheimer's. We know all know the symptoms, and I think it's very sad because I think the life is taken away from the person. You can't remember really your past and what you have done, what you have achieved. And also here in the statistics, you can see that not only from Alzheimer's, but other brain disorders, that they are emerging as the leading contributors to global disease burden. And here in Europe, currently, 35% of brain disorders actually is overall, the percentage overall, the other diseases. And the percentage of US citizens is actually 2.4%. They have, what, 200 million? So you can imagine how many people have Alzheimer's there. And the cost is crazy. An accumulated cost of 200 billion, and that's not only because the drugs, they're not treatment, they're actually symptom relief drugs. And also, you need constant care, so you need constantly nursing of the patients. What I'm looking at really is in the molecular level, how the cells in the brain communicate. So in the brain, you have neuron cells and non-neuron cells. Here, what I'm interested in is that when a signal starts in a presynaptic neuron, which let's call transmitter cell, we want to send information to a postsynaptic neuron, which is we call receiver cell. When the signals get to the terminal, glial transmitters are being released in that synaptic channel. And this synaptic channel is like a wireless channel where molecules flow from one cell to the other, but a very short range. And these glial transmitters are actually the carriers of the information. What happens is like when this third cell, astrocyte, which is also responsible for providing these glial transmitters, starting to fail. And that's because the internal regulation of calcium signaling of this cell, of the astrocytes, and even the networks, also starts to fail. And that causes a lack of, or maybe too high glial transmitters is being transmitted, and that impacts on the synaptic plasticity, which means the connection is going to break or they're going to firmly stay there. In Alzheimer's, what happens more precisely in the astrocyte, of course, the calcium is regulated in the cytosol, so you have organelles and that regulates this calcium, of course, inwards and outflows of this calcium. And in Alzheimer's, there is this protein called amyloid beta oligomer that affects the mitochondria. And the mitochondria starts producing too much of calcium, which will cause apoptosis and ultimately, when disease spreads, cause Alzheimer's. So I'm actually a communication theory, come from engineering. So when I was studying this, they're always telling about this hypothesis, but they're never proposing like, how can we control such a thing? Maybe one or two after that recently having me proposed as well. And what I'm looking at really is how can I achieve great values of this calcium? How can I set this calcium to a particular level, which enables me to have some controlling of the synaptic activity as well. So far I have come up with this system, whereas if you know the values of the calcium and the protein that activates calcium, which is the IP3, you can actually generate a new value of IP3 that will give you a desired value of calcium. And how to generate these IP3 levels? You can actually stimulate the cell electrically, like with some deep brain stimulation, but also can stimulate the cell chemically and mechanically. So first results actually, but the blue line is actually the activity of the cell, the calcium activity of the cell. And the dashed yellow line, if you can see, is the proposed control theory. And we actually could achieve, after very few seconds, stabilization of this value and eliminating the oscillations. Even when we have irregular oscillation, which is more the case of Alzheimer's, we can actually stabilize this. We can see this as a potential new treatment, and we believe that this integration of deep brain stimulation can move forward this treatment for this disease. And now, how to implement this? We are looking actually up to genetics, and the reason for that is that enables single neuron stimulation, but also single cell basically stimulation, or astrocytes or microglia. And the original approach actually used optical cables. I don't think it's really feasible for us humans to keep using optical cables as treatment, or go to the hospital and you have to put an optical cable. But then we are proposing wireless optogenetics nanonetworks. So these guys in Berkeley designed the WIT neurodust devices, which are nano devices that has a LED, and these LEDs emit light. And this light will stimulate all the neuron on the astrocyte, in our case, the astrocyte. So we thought in a way that how about we control these nano devices, or the stimulation of the brain, basically, from the outside. So we propose this 3-layer architecture with an external transceiver, a subdural transceiver, which is right below the skull, and they connect with these nano devices using ultrasound signals. And the ultrasound is known to penetrate the tissue of the brain and do not cause any damage. In this way, we want to now connect the two worlds, right? We want to connect the control of the astrocytes, which people already have started doing experiments, and also the optogenetics. These guys recently have proposed, which calls the really impacting neuroscience, using near-infrared, right, for deep brain stimulation with nanoparticles. With our approach, we believe that we can make this more flexible. We can also look into adding information to the brain. I don't want to talk much about it, cause much excitement, but we believe also that the wireless optogenetic nanonetwork can be used for different applications. And I'd like to thank the Irish Research Council for funding TSSG and all the other partners as well, and you guys for listening.
Thank you, Michael. Does anyone have any questions for Michael? Hold on 1 second.
I think it'd be pretty cool walking around with all of these wires coming out of your head, but particularly on a Friday night, you wouldn't notice much difference with normal people going out. I suppose the question is, the approach that you're taking is really exciting. Though when you actually put the nano device into the brain itself, how can you make it unidirectional so that you know that the signal is going to the right part of the brain?
Well, this is a very important question, and this comes to another research that we're starting at TSG, trying to infer the topologies of the brain. And like in computer networks, you have many approaches to infer the topology of even ad hoc networks. But if we could bring this technology to the brain as well and try to infer the connections, then we have the key for your question. But right now, what we can do is actually use a mixture of EEG and MRI, and this gives us at least where areas and particular areas in the brain that are failing, because the initial proposal of optogenetics is to deal with aneurysm, so failures of neural networks, basically. But yeah, that's basically how to answer your question. But again, far away from being actually a treatment.
Any other quick questions? No? Okay, that's super. Thanks so much, Michael.